Hello students, welcome back to our journey through integrals. Let me ask you something simple. Have you ever tried dividing one number by another, say 22 by 7? You know it never ends, it keeps going into decimals. Something similar happens when we divide one polynomial by another. The result is called a rational function. Improper rational functions can always be reduced to proper ones using long division. And that's the starting point of partial fractions. So how do we reduce an improper rational function? It's simple. We divide the numerator by the denominator, just like we did in school with ordinary numbers. The result looks like this. P of x over q of x equals t of x plus p1 of x over q of x. Here, t of x is a polynomial, and p1 of x over q of x is now a proper rational function. Once we've done this step, the problem is much easier. We can integrate t of x directly and then focus only on the proper rational part, p1 over q. So how do we reduce an improper rational function? It's simple. We divide the numerator by the denominator, just like we did in school with ordinary numbers. The result looks like this. P of x over q of x equals t of x plus p1 of x over q of x. Here, t of x is a polynomial, and p1 of x over q of x is now a proper rational function. Once we've done this step, the problem is much easier. We can integrate t of x directly and then focus only on the proper rational part, p1 over q. Now let's see what happens with proper rational functions. The idea is to split them into smaller, easier fractions, and that is what we call partial fraction decomposition. The denominator decides the structure of these partial fractions. If the denominator has linear factors, we get terms like a divided by x minus r. If it has irreducible quadratic factors, we get terms like bx plus c over ax squared plus bx plus c. The unknown constants a, b, and c are found by equating numerators. Once decomposition is done, the integral reduces to standard formulas. Let's begin with the easy case, linear factors. Suppose in decomposition we have a term like a over x minus r. The integration is direct. The formula is integral of a over x minus r with respect to x equals a log modulus of x minus r plus c, that's it. Each linear factor always leads to a logarithmic result. So, if your denominator splits into distinct linear factors, you're in luck. The answer is just a combination of logarithms. But what if the denominator has quadratic terms that cannot be factored further? In that case, the partial fraction looks like bx plus c divided by ax squared plus bx plus c. We then split it into two parts, bx over ax squared plus bx plus c and c over ax squared plus bx plus c. The first part is handled by substitution, while the second part uses a standard formula. That formula is integral of dx over x squared plus a squared equals 1 over a tan inverse of x upon a plus c dot. So whenever you see an irreducible quadratic, expect a mix of logarithms and arctan terms in your final answer. Let's do a concrete example to see this in action. We want to evaluate the integral of dx over x squared minus 1. Step 1. Factor the denominator. X squared minus 1 factors as x minus 1 into x plus 1. Step 2. Decompose. We can write 1 over x squared minus 1 as 1/2 into bracket 1 over x minus 1 over x plus 1 bracket close. Step 3. Integrate each term separately. Integral of 1 over x minus 1 dx equals log modulus of x minus 1. Integral of 1 over x plus 1 dx equals log modulus of x plus 1. Step 4. Combine. The result is 1/2 log modulus of x minus 1 divided by x plus 1 plus constant c. See how nicely the partial fraction method transformed a difficult integral into simple logarithms? Now let's pause and think, why is this method important beyond exams? In calculus, it allows us to solve any rational integral systematically. In Laplace transforms, partial fractions are the backbone for breaking functions into invertible parts. In electrical engineering, they are used to analyze complex circuits. Even in physics, rational functions appear in motion, wave, and energy models. So, partial fractions are not just about exams, they are about real-world applications too.